This is problem 1382. It's on page 751. Cold water leading to a shower enters a thin-walled double-pipe counterflow heat exchanger at 15 degrees Celsius at a rate of a quarter kilogram per second and is heated to 45 degrees Celsius by hot water, which enters at 100 degrees Celsius at a rate of 3 kilograms per second. If the overall heat transfer coefficient is 950 watts per square meter per degree Celsius, determine the rate of heat transfer and the heat transfer surface area of the heat exchanger using the effectiveness number of transfer units method. Now there's a lot of properties given there I did not read. I will jot those down. You might want to refer to the problem statement as I go along to understand where all of the numbers I write down come from. So let's see. This is a double pipe heat exchanger, so it's a fairly simple, straightforward heat exchanger. There's the inner pipe. Let's try that again. There we go. And we know that we have a heating fluid at 100 degrees Celsius. One of the pieces of information given about it was the heat capacity is 4190. I'm out of space, joules per kilogram per degree Celsius. So there's the heat capacity on the hot side. The mass flow rate on the hot side was given as 3 kilograms per second. Now, let me put a little dividing line here because we have a stream coming out here that is coming out at 45 degrees Celsius. The cold stream comes in here at 15 degrees Celsius on the shell side, and the heat capacity on the cold side is 4180 joules per kilogram per degree Celsius. Now notice these two are pretty close to each other. The heat capacity of water does change with temperature, but it's not a huge change. The mass flow rate was a quarter kilogram per second on the cold side. And notice that we don't have the exiting temperature of the hot stream. The overall heat transfer coefficient U was given as 950 watts per square meter per degree Celsius. Now we're constrained to use the effectiveness number of transfer units method here, but you could use the log mean temperature difference method. The way you would do it is set up an energy balance, realizing all the energy that comes out of the hot stream goes into the cold stream. You know the temperature change and flow properties of the cold side, so you could actually calculate the rate of heat transfer into the cold side, and all that heat transfer must come from the hot side. So you could actually get the exiting temperature of the hot side. I'll leave that for you as an exercise. But we're going to solve this using the effectiveness number of transfer units method. Now, the effectiveness number of transfer units method revolves around finding the effectiveness and the number of transfer units to solve the problem. To find these things, you need a couple of other pieces of information along the way. One in particular is the capacity rate. Now, the capacity rate, C, is the ratio of, excuse me, I misspoke. The capacity ratio is the ratio of the capacity rates. The capacity rate that is the smaller over the capacity rate that is the larger. Now, I know this is confusing. This capacity ratio is something very different from these two. These two both have units. Even though they both have the character C, that's a different C than this. This is the ratio of these two. So some people even put a subscript R there to make it clear that it's the capacity ratio. I think it should be given a different letter, but it's not. So there we go. So the capacity rates, well, what are those? Well, the capacity rate on the cold side is the mass flow rate on the cold side times the heat capacity on the cold side. The capacity rate on the hot side is just the mass flow rate on the hot side times the heat capacity on the hot side. Now these are pretty easy to come up with because we've been given all this information. So the mass flow rate, quarter kilogram per second on the cold side, heat capacity on the cold side, 4180 joules per kilogram per degree Celsius. Plug all that into your calculator and you'll find the capacity rate is 1.045 kilojoules per second per degree Celsius. That's on the cold side. On the hot side, the capacity rate is different. There's 3 kilograms per second of flow, and the heat capacity is 4190 joules per kilogram per degree Celsius. And so this number comes out to 12.570 or so kilojoules per second per degree Celsius. Obviously, there's a huge difference in the capacity rates on the hot and the cold side. And it's also apparent which one's the minimum or the smaller and which is the maximum. So 1.045 kilojoules per second per degree Celsius is C min. C max is 12.570, and I won't put in the units because they will cancel and become dimensionals for this capacity ratio. So the capacity ratio is about 0.0833134. Way too many decimal places, but there it is. Okay. Now we could actually calculate the heat transfer rate at this point. That's pretty straightforward. The heat transfer rate is simply the capacity rate on the cold side, because notice I know the temperature change on the cold side, multiplied by that temperature change. Temperature of the cold stream out less temperature of the cold stream in. Okay. So that's 1.045 kilojoules per second per degree Celsius multiplied by 45 less 15 degrees Celsius. Notice that's the temperature change. It goes from 15 to 45 degrees. So the degrees Celsius go away, and the heat transfer rate then is about 31.35 kilowatts. Now we're supposed to find the heat transfer rate, so there we have it, but we're also supposed to find how much surface area is required for this heat transfer rate. Notice we were not given the size of this heat exchanger. We were not given the amount of surface area. So this is part A. We're done with part A. Part B, the question is, how much area is required? Well, the number of transfer units is simply UA over C min, where C min is the minimum capacity rate. The minimum capacity rate we already know is 1.045, so that's taken care of. U, the overall heat transfer coefficient, was given in the problem statement. So really, I forgot a U there on my NTU. So really, to calculate the area, if we had the number of transfer units, we could calculate the area, right? Okay, so if we have the number of transfer units, we already have C min, we have the overall heat transfer coefficient, we could find the amount of area required. Now, the nice thing about the effectiveness number of transfer units method is that there are equations, instead of using a chart like in the log mean temperature difference method, there are equations for coming up with, well, basically relating the effectiveness to the capacity ratio and to the number of transfer units. Now you have to decide which set of equations you need. Page 729 includes several equations, table 13.4, and there's another one on page 732, table 13.5. We have to decide which of these we're trying to use. Notice, as I said, we could use the log mean temperature difference method here, because if we took our heat transfer rate, we could calculate the exiting temperature on the hot stream side. So then we'd have all of our temperatures, we could use the log mean temperature difference method. So apparently the set of equations we need to use are the ones on page 732. If you don't have a note on table 13.5, page 732, you need to add one now. And that note would say that these equations are used in lieu of, or instead of, the log mean temperature difference. So we're trying to find the number of transfer units. Fortunately, there's plenty of equations here to find the number of transfer units, but we have to select the correct one. Now, obviously, this is not a cross-flow heat exchanger. It's also not a heat exchanger with a capacity ratio of 0. We know the capacity ratio is small, but it isn't 0. So equations under 3 and 4 are not applicable. This is, however, a double pipe heat exchanger. Is it parallel flow or counterflow? Well, if you look, the hot fluid flows through the pipe in this direction from left to right in my drawing, but the shell fluid flows from right to left. So this is in fact counterflow. So the equation that we need to use is under section 1, counterflow, where we've got the number of transfer units in terms of the capacity ratio and effectiveness. So let's see. Now you have these hopefully all in your notes by now. So let me continue part B up here and say the number of transfer units is just 1 over C less 1 multiplied by the natural logarithm of the effectiveness less 1 divided by the effectiveness times the capacity ratio less 1. Okay, so this is the correct equation to use. I got it out of table 13.5 on page 732 under the double pipe counterflow heat exchanger. But notice we're missing something. We don't know the effectiveness yet. Now, what is effectiveness? Effectiveness is the actual heat transfer rate over the maximum heat transfer rate. That's what effectiveness is. Now we've got the actual heat transfer rate, but what's the maximum heat transfer rate? Well, the maximum heat transfer rate, Q dot max, is the minimum capacity rate multiplied by the maximum temperature difference around the heat exchanger, and that will always be the temperature of the hot stream in less the temperature of the cold stream in. Now let me erase this bit down here. So calculating the maximum heat transfer rate, that would be 1.045 1.045 kilojoules per second per degree Celsius multiplied by 100 degrees Celsius less 15 degrees Celsius. Notice the cold stream comes in at 15, the hot stream comes in at 100, so that's the difference we need. And I forgot my degrees Celsius on the 15, there we go. So the maximum heat transfer rate would be 88.825 kilowatts. So now I can actually calculate the effectiveness. The effectiveness was 31.35 kilowatts. The maximum heat transfer rate is 88.825 kilowatts. Both go away. Of course, effectiveness is dimensionless, and this is about 35% effective. I don't know why I carried so many decimal places through my solution, but there it is. So about 35%, 0.35, 29, and so on. That's the effectiveness. So now we can actually calculate the number of transfer units. Now this is really what we came for, so I'll just remember I'm going to plug it in here. The capacity ratio was that 0.083134 number. We have to subtract 1 off of it. Take the natural logarithm of the effectiveness less 1, 0.352941 less 1, divided by the effectiveness, 0.352941, multiplied by the capacity ratio, 0.083134, less 1. So notice, of course, the multiplication has to be performed before the division. I apologize if that ran off the video screen. You should be able to plug the numbers into the equation pretty easily. This comes out to about 0.4423, and it's dimensionless. It's the number of transfer units. So now we can plug that in here. Notice the minimum capacity rate is still the 1.04. Tell you what, I'll just go ahead and plug it in above so that you can see how it works. So the area would be number of transfer units, 0.4423, which is dimensionless, multiplied by the minimum capacity rate, 1.045 kilojoules per second per degree Celsius, divided by the overall heat transfer coefficient, 950 watts per square meter per degree Celsius. Now you have to be a little bit careful here. A kilojoule per second is not the same thing as a watt. A kilojoule per second is in fact a kilowatt. So we need to either convert that to watts or convert the watts to kilowatts. I just converted the watts to kilowatts. A kilowatt is 1,000 watts, so the watts go away, the kilowatts go away, the degrees Celsius go away. You see that we'll end up with square meters for the area. The area comes out to about a half square meter of area. So we know the actual heat transfer rate. It's about 31 kilowatts or so, and the area we need is about a half square meter.